All right, so the central limit theorem, great. So now we have a way to build standard errors for estimators that are means. But what if I am trying to estimate something that's not a mean, right? Any other thing? How do I get the standard error of that? The one way to do that is with this thing called the delta method. So this is now, I'm going to talk about a couple things that you don't really have to know how to use. It's more like to recognize how to do this. Because in practice, what you're going to see is like this, right? You're going to see, here's the estimate, and then here's the estimated standard error. And it's just going to be somebody's going to give you a formula. But what I want you to be able to think about is like, okay, how did they get this, right? Well, what they did is that they had this estimator, and then they had to figure out what the true standard error of this thing is, right? And I want you to ask yourself, well, did they make any assumptions in order to derive this true standard error? Did they have to make any assumptions about the data generating process? And if so, are those assumptions legit? Or did they have to assume crazy shit like, oh, pretend Z is normal? Like, you don't know that. So if you have to pretend anything like Z is normal, or these things are independent, or whatever, in order to derive what this true standard error is, then it's probably bullshit, right? And then going from the true standard error to the estimated standard error, that's normally like pretty straightforward thing. You just do like plugins or stuff like that. But in the wild, you're just going to see some formulas, right? And it's up to you to kind of peel the layers back a little bit and be like, okay, how did you do this? Even if you're not the one who's going to do it, I want you to understand how they did it, what the arguments are, so that you can kind of critique that to the best of your ability. And of course, you're not totally on your own, right? Like you can call for help, call a statistician, but like honestly, most people don't understand this, and so that's why sometimes you kind of are on your own. I wish it weren't like that, but sometimes you are. Because this is very tricky. It's very tricky, and since most people don't get it, you kind of have to be, the captain of the ship sometimes, and be like, well, I'm the adult in the room, and so I'm going to figure out how this works. And I mean, you're going to school at Berkeley, so that when you graduate from a place like this, very often you are the kind of leader, you are the adult in the room, and that's why we have to do this. All right, so getting back to the story that I was going to say here, like. So now we're asking about how do we extend the central limit theorem so that we can use it somehow to like guess at the true standard error of estimators that are not just simple sample means. So what we've shown is that basically if you blow up an estimator, let's say this is a sample mean by root n, that thing starts to look like this normal. Okay, so if I know that, what if I have this estimator that's a function of some sample means? What's the distribution of that? And it turns out that there's a formula that you can use. So if the mean of this sample mean is mu, then the mean of g of mu is going to be g of mu hat is going to be g of mu. And what's the variance? This is the important part, right? In terms of building confidence intervals, the standard error. All you need to do is multiply that standard error by the derivative of g, and here you would evaluate it at the value mu hat. So that's kind of complicated. So let's just look at an example. And again, you're not really going to have to do it. It's just mainly like recognizing. So let's say we're interested in the log mean value of some measurement. So like income in a particular population. Let's say people are interested in the log of the mean of that, because that income is so highly skewed, and so it might be kind of a not as interpretable to look at just the mean. So what's the natural plug-in estimator here? Well, you would just take the sample mean, and then you take the log of that, okay? And we want to know what's the asymptotic variance of, like, let's say I have some samples of data, right, of income, and I can calculate this thing, great. But I want to know how uncertain is it? How can I find the asymptotic variance, right? Well, I know what I have to do if I want to build a confidence interval is find the asymptotic variance, divide it by n, and then take the square root of that, and then add 2 times that thing, plus or minus the estimate. There's my confidence interval, 95%, great. But to do that, I had to know what the asymptotic variance of this estimator actually is. So how do we find that? So that's the question. And then, secondly, well, it's actually kind of like coded up. and make it go. So our estimator psi hat is the log of 1 over n. Sorry. So this guy here is a sample mean. So we can call that mu hat. And so this is log of mu hat. And I know that mu hat times root n has, by the central limit theorem, because this is a sample mean, this has to have some distribution like this, where this is the standard error. In fact, I know what this is. This is going to be x, and then the standard error will be the variance of x squared. Okay. So how can I use that? How can I then find the sampling distribution of the log of that? Well, what the delta method says is that if I want to know the sampling distribution of log of mu hat, that will be by just looking up the formula, which is, it says, so here, I'll just put what the delta method says. If you haven't seen this before, this is just a little abbreviation for the derivative of g, and then whatever this is. And since I'm writing that here, like that. This is what the delta method says. If I'm not mistaken. So let's just check that. Looks right to me. So in this case, this g function is log. That's it. So that tells us that this thing, root n of log of mu hat, which is our, this is psi hat, this is our estimate, is going to be have a distribution that is normal with here this g is log of whatever the mean of x is, which, I mean, this should make sense, right? If I'm estimating the log mean income, the average value that I should get for that is actually the true log mean income. That's what this says. Which is like, if this were not the case, then it would be very bad, right? And then here we need the derivative of log, so we can figure out what that is. One over x. Okay. So what that means for us is that this is 1 over mu times, and then here, yeah, again, I should be writing e of x to be consistent, times variance of x. And that's it. So this is if the asymptotic standard error of this mean, sample mean, is this, then the asymptotic standard error of the log of that sample mean is going to be this. So the variance of x, square root of variance of x divided by whatever the mean of x is. Which is kind of interesting. So let's see if that works out, actually. Well, let's just use this simulation here. So we already have x here, right? And although here it's going to be a problem, so I'm taking the log. This is not a not strictly positive. So let's just say x. Let's just take the absolute value of that, and then add 1/2. Something like that. Okay. Just show you what that looks like. That's a distribution. Okay, cool. Whatever. So this is a funny looking random variable, and it has that density. And now what I'm interested in is not estimating so here my estimator, I was using the mean of x, right? Now my estimate is the log of the mean of x. Okay. And this is still the same, so let's run that. So now the true variance, what is the true variance of x? Okay, it's about a quarter. We already saw the density. So now we can do this same thing. I think nothing should change here. Great. So here what I'm going to do is I have my estimate of the log of mean of x. And I should also have no, I'm sorry. Let's just do this. Just do this like this. Let's generate the sampling distribution. Okay, and we can look at the plots. Look at that, all pretty normal. Even though we're looking at now the log of the mean, not the mean itself. So interesting. And now let's look at the actual variance of that log of the mean of x. That's what we have here, the empirical variance, log of the mean of x. And then here, this is wrong, right? Because we have variance of x divided by n. This is the predicted variance for the mean, but now we want the predicted variance for the log of that mean, which, according to our math, should be the expected variance of x over the expected value of x. So we need to calculate what the expected value of x is, and then it's all that divided by n. So what is the expected value of x? It's just mean of x. Okay, cool. So here, hopefully that comes out right. No, need a premises. Yes. Okay, success. Great. So so these numbers again for small sample size, we're seeing some discrepancies, right? But as the samples get bigger and bigger, these are actually coming pretty close together, right? So now the error is like in the 4th decimal point here, and then here this is actually a very small difference, right? Like 9 versus 10. So the differences are getting smaller and smaller. So this is in fact, yes, this is the predicted variance. This is the true. So what we've come up with is a formula. Just take the variance of x divided by the mean of x. We don't know what those are, but in theory, if we know the data generating process, this is what they are. So what we've come up with here is a formula that we relate the data generating process to the standard error, which is the true variability of our guess. So we know what algorithm we're using to guess. So we're using a sample mean. If we know the data generating process, then we can analytically compute this kind of a standard error, right? Except here we were doing it when the estimator is just this simple sample mean. Now we can do it when the estimator is any kind of function of a sample mean. It just takes a little bit of math, but this works. And again, you don't really have to do this; just be able to recognize that this is possible.